Assalamualaikum warahmatullahi wabarakatuh. We are from group 2. We're gonna present topic about ceramic, which is material, structure and processing. What are ceramic? Ceramic are combination of one or more metallic elements with one or more non-metallic elements. Metallic elements in predictable in the light color one and non-metallic elements in the predictable in dark color one. Ceramic are most often silicate, oxide, nitrides and carbide. This compound gives ceramic their strength and stability. Unlike metal, ceramic don't allow electricity or heat to pass through them easily. That's why they are used as insulator in electronic and in kitchenware that resist heat transfer. Ceramic can survive extreme heat and corrosive environments better than metals or plastic. For example, spark plugs and furnace lining rely on this property. Ceramics are very hard, but they are also brittle. Think of like tile floor, it's tough to scratch, but if you drop something heavy, it can easily crack. Now, let's talk about silica glass, which is basically a dense form of amorphous silica. In its structure, there's a charge imbalance. To fix this, counter cation like sodium ion Na+ are added. This will stabilize the glass network and make it usable. But all glasses are the same. Sodium glass, the type used in windows and bottle, is cheaper but more brittle and less stable at high temperatures. Borosilicate glass, which we know as pyrite, is tougher, resistant to shock, and it's widely used in laboratories and also cookware. Here's I also add a table, which is a quick comparison between sodium glass and also borosilicate glass. Sodium glass has lower durability, more brittle and common in window, bottles and others. Borosilicate glass has higher durability, less brittle and used in labs and ovens. This difference explains why pyrite doesn't crack when you pour boiling water, but a normal glass might. Silica glass is one of the most important ceramic materials and it has some very distinctive properties. First, the melting temperature of glass is moderate compared to other ceramic, which make it easier to work with. However, it has low toughness and ductility, meaning it can break easily. On the positive side, it has high stiffness or large monoline and excellent resistance to creep, which means it doesn't deform much under long-term stress. The second one is application. Because of this property, silica glass is used in high temperature environment and where resistance is needed. It's charged neutrality and also open up novel uses such as in specialized electronic and also optical devices. The third one is fabrication. One big advantage is that some types of glass can be easily formed or shaped. Think of like glass blowing or industrial molding. In contrast, most other ceramic cannot be cast or formed this way, which makes glass unique among ceramic materials. So, silica glass combines moderate work ability with high resistance, making it versatile for both everyday uses and advanced applications. Glasses are transparent and can be easily shaped. For non-crystalline, their atoms are arranged randomly rather than in a repeating pattern. They are mainly made from silicates combined with oxides such as calcium oxide, sodium oxide, potassium oxide, and aluminium oxide. A common example is soda lime glass, which is contains 70% silica and 30% soda and lime. Here we can see table 14.1 composition and characteristic of some of the common commercial glasses such as fused silica and also borosilicate known as pyrite. Ceramics are different from metal because their structure are mainly ionic. That means they are built from charged ion, positive cation and negative anion. Cation are positively charged metal ions, while anions are negatively charged non-metal ions. Together, they form the repeating crystal structure of ceramics. There are two key factors that decide how the crystal structure forms. The first one is charge balance. The overall structure must be electrically neutral. If the charges don't balance, the structure isn't stable. The second one is relative ion size. The size of the cation compared to the anion determines where the cation fit inside the lattice. Small cation can slip easily into spaces between larger anions. These rules explain why ceramics can have different crystal structure like rock-style or perovskite and why each structure gives ceramic unique properties such as strength, retinence, or conductivity. Example of crystal structure. The first one is rock-salt structure. For example, NaCl, sodium chloride, that commonly known as table salt. The second one is fluoride structure. For example, calcium chloride, that naturally occurs as the mineral fluoride. The third one is perovskite structure. For example, barium titanate, that widely used in capacitors and also electronic. And the last one is spinel structure. For example, magnesium aluminate spinel, that can be found in gemstones and also refractories.
So next, we move on to the basic structure of the ceramics. In most ceramics, oxygen ions are larger than metal ions. So what happens is, oxygen will form a tightly packed structure, which is fused and then the smaller metal ions will occupy the empty spaces between them. So this structure, this arrangement is very important because it electrical neutrality of the overall structure, which the total charge must balance the crystallographic arrangement. The arrangement must be stable, and fourth, correct stoichiometry, which we must watch the ratio match the formula. So in this slide, we want to compare the crystalline and also non-crystalline structure. So between this, quartz is a crystalline, meaning the atoms are arranged in a repeated pattern, while glasses is a bit different. It is amorphous. It does not have a long range or dead structure. So for fused silica, it is a pure silica oxide, which is no impurities. And for other glasses, normal glasses contains Na+, Ca2+, Al3+, and also B3+. So next, I will explain the basic unit for silicates, which silicates are made by linking SiO4 together in a tetrahedron shape, which is silicon at the center and bonded to 4 oxygen around it. So in this slide, it shows 3 different shape, 3 various structure, which is Mg2SiO4, Ca2MgSi2O7, and also Si3O9. Next, for layered silicates, which we also call clay silicates, are SiO4 tetrahedra connected together to form 2D plane, which shared by corners, edges, and also faces. So in this case, it shows the Si2O5 2 negative. So since it is negatively charged, it needs positive ions like calcium or magnesium to balance the charge and also stabilize the structure. So this slide shows one of the example for layered silicates, which is kaolinite clay. So it consists alternating layers of silicates and also aluminium hydroxide. And these layers are weakly bonded by van der Waals forces. Since it is bonded by weak forces, it can easily slide, make the clay soft and also moldable, which is easily to shape. So next, the slide shows the layered silicates properties and applications. So these layered structures are very flexible. We can change the ions between layers, which changes the spacing. Also, water can enter these layers, making the material to expand. So in this case, it shows 2 examples. First, mica and also bentonite. Bentonite is very useful in industry because it is used to seal wells because it expands and prevents contaminated water from leaking. Carbon can also form a ceramic-like structure. For instance, carbon black. Carbon black is a amorphous structure and also has a very high surface area, which is 1000 m2 per g. So this is it's very useful for applications like adsorption and also as a fillers. And next, diamonds. Diamonds have a tetrahedral carbon, and it is very hard, very brittle, and also doesn't have any slip plane. And there are 3 categories for diamonds, which is large diamonds, small diamonds, and also diamond films. So for large diamonds, the example is jewelry. Small diamonds, cutting tools, which is often man-made and used for polishing. And lastly, diamond films. It is a very hard surface to it and also used as cutting tools and medical devices.
So for the next carbon forms is graphite. Graphite is one of the atoms of carbon where carbon atoms are arranged in a unique layered structure. In graphite, each carbon atom is bonded to 3 other carbon atoms in a flat hexagonal pattern. These form layers of hexagonal rings. These layers are very strong because the atoms are connected by strong covalent bonds. However, the layers are held together by weak van der Waals forces, so they can easily slide each other. This is why graphite is soft and can be used as a lubricant. For fullerenes is another form of carbon where the atoms are arranged in a closed structure, such as sphere or tube. The most common example is C60, which look like a football shape. Each carbon atom is bonded to 3 other atoms using covalent bonds. This forms a strong but lightweight structure. Other than that, fluorines have unique properties such as high stability, ability to act as antioxidants, and potential use in medicine and nanotechnology. For carbons, nanotubes are cylinder structure made from rolled-up graphene layers. Like graphite, each other carbon is bonded to 3 others in hexagonal pattern. They have very strong covalent bonds, which make them extremely strong and lightweight. For preparation of raw materials, we need crushing and grinding, which is to get ready ceramic powder for shaping. So the first one is crushing, which is breaks large rocks or raw materials into smaller pieces, so they can reduce the particle size roughly. For grinding, it further reduces particle into fine ceramic powder, so it can produce a smooth uniform powder for processing. For clay composition, we have 3 components. So the first one is 50% of clay, which is aluminosilicate. This is the main material that gives shape and plasticity. Clay is mainly made of aluminosilicate, which contains aluminium, silicon, and oxygens. The next component is 25% of filler, which is quartz. SiO2. Quartz is added to improve strength and reduce shrinkage during heating. So the last one is 25% of fluxing agent, which is feldspar. So feldspar helps to bind the particles together when heated. It contains ions like K+, sodium+, and calcium 2+, which help in melting and forming a glassy face. So for powder processing, a ceramic powder is converted into a useful shape before heating. So it has 3 processing techniques. So the first one is tape casting. Tape casting is used to produce thin ceramic sheets. A slurry of ceramic powder is spread into a thin layer and then we dry. For second one is slip casting, which is involved pouring in a liquid mixture of ceramic powder called slip into a mold. The mold absorbs water and leaves a solid ceramic layer. So the last one, the last step is injection molding. So injection molding mix ceramic powder with a binder and injects it into a mold to form complex shape. So move on to a features of a slip. So firstly, clay is inexpensive and widely available, which makes it suitable for ceramic production. So why we add water? Because when water is added to a clay, it can change its behavior of the material. The water reduces the attraction between clay particles. Because the bonding between layers is weak, mainly due to weak van der Waals forces, the layers can easily slide over each other. So this is why we call it shear. So for structure, kaolin is a clay. It's made of layers that are charge neutral, like Si4+, aluminium 3+, or H- and O2-. These layers are held together by weak van der Waals forces, which makes slipping easier. So adding water improves the workability of clay by reducing bonding forces and allowing easy shaping. So the last one is injection molding. We have 2, which is hot injection and cooling solidification. So firstly, raw materials are mixed with resin, which is fusion, to provide the necessary fluidity degree, which is in the pellet heater. And then we inject it into the molding die. And then the mold is cooled to harden the binder and produce a green compact part, which is also known as an unsintered powder compact. That's all from us. Thank you.